Thanks. I'm Rob. This is Guy, and we're developers from Shopify. Shopify is a SaaS commerce platform that really is about helping merchants sell on a variety of channels, online, social media, and retail. And we're on a team that really focuses on API tools and infrastructure to kind of have a public API platform. And GraphQL is a major focus of that. We've been using GraphQL since 2016. Really started with the storefront API and expanded to different use cases since then. Each of these different use cases have a lot of different characteristics and trade-offs, but really for the majority of our APIs, they're public, and we have different audiences that use them for different ways. But we still think GraphQL is an ideal fit because a client can kind of describe their data requirements for their own use cases. It's really the basis of a flexible, extensible platform that really lets a merchant customize the commerce stack for their needs. We're primarily a Ruby monolith company, so we use GraphQL Ruby as kind of the server language to kind of achieve the GraphQL server. And I just want to acknowledge the great work Robert Masalgo has done as a solo maintainer, kind of maintaining that gem. To kind of focus on performance, it's a broad category, so I'm going to kind of narrow it down to the GraphQL slice. So I kind of want to talk through the different phases of execution. We have lexing, parsing, static validation, and execution. Really, at the end of the day, we want to minimize the time that we're spent that is not doing business logic. So if we have to do any GraphQL overhead, like lexing and parsing, we want to make that short and as fast as possible. So let's talk about lexing and parsing for a second. So quite often, you'll see a GraphQL client sending a query string to the server, and the server needs to understand its contents. So the start of that process is lexing. We're taking the query string, and we're scanning through it from left to right and building a sequence of tokens. So we end up with an array of tuples with a symbol and a value. There's no awareness of the GraphQL schema definition. We're really only aware of the GraphQL grammar. What are the special characters as defined by the spec? After we lex, we then go to parsing, where we're iterating through these tokens left to right to build an AST abstract syntax tree. This is kind of where we start to look more like a tree in the GraphQL sense of a graph. So for us, one of our key operations is in the checkout space. We actually had a large document with over 3,300 lines to it with 330 fragments. So this actually had a long time to lex and parse. We were seeing 25 to 30 milliseconds, which isn't great. That's a lot of overhead just to understand what the client wants to do. And you do that on every request. So we were like, can it be faster? Thankfully, lexing and parsing are really well understood spaces in the in the computer science space. So we have a lot of different options that we can compare based on other languages too. So the default for GraphQL Ruby's gem is to use another gem called rack. Rack is a look ahead with one token from left to right parser generator. So really, you write a grammar for rack. Rack is then going to compile or make a parser on your behalf. And this is really, it's going to make a state machine with some idea of do this action when I'm in this state. So for us, we have the option to look at a Ruby implementation that rack makes on our behalf or a C-based implementation. So our first step was like, let's compare these two options because these are very one-to-one comparisons. Beyond that, we actually looked at a couple other ones too. So I just want to kind of outline the different things that we explored so far. So we have rack, which is pure Ruby-based, so it's only using Ruby. Our rack using a C extension, so our entry point to the parser is Ruby, and then our main state machine logic is C code. But then the C code has to say what is the next token to understand what to do next. So I was actually going back to Ruby code. So there's this like tight loop between the two languages, a lot of back and forth. So a lot of switching may not be the best. Then you have Yak, yet another compiler. So that's basically a pure C-based parser. So the entry point is Ruby, but it's calling into a C extension, the parser, and all the logic to understand what to do next, get the next token, is all done within C. We also had someone at Shopify write Tiny GraphQL. It was an experimental, handwritten, recursive descent to parser that we thought was very specific to our use case. So we thought, let's explore that. And then we also have another factor called YJIT. YJIT is a just-in-time compiler. It's a very minimalistic Ruby JIT built inside of C Ruby. Originally it was created at Shopify, but it's since been open sourced, and it's actually upstream into Ruby 3.2, so anyone can use it. It's basically like a flag that you run your code with. So for us, we were wanting to compare this slow operation in checkouts and see how these different lexing, parsing implementations compared. So when I was first making the graph, I actually made a mistake. I thought that rack by default was using a C extension in GraphQL Ruby. So that's kind of our baseline here in the blue line on the left. So everything is relative to that. Is it slower or faster than that as a baseline? In reality, GraphQL Ruby is using the pure Ruby-based implementation, the second bar, the green bar. So it's actually even slower than I thought. So that was like our baseline in production. We found that by switching to Yak, we could actually achieve a 7 times speed up. So we went from like 25, 30 milliseconds down to less than 5. So that was a quick win for us because this Yak compiled C parser actually is an alternative single line replacement with our GraphQL Ruby gem usage. So it's very easy just to switch one out for the other and just get faster code. But you have to choose to do that. It's not something that's automatic. So if you do happen to use GraphQL Ruby, definitely look into the C parser. You can definitely get some wins there. So really, one thing I took away from this was just that when you do switch languages back and forth between like Ruby and C and back and forth, especially in like a tight loop, the just-in-time compilers have a hard time optimizing that. So if you can kind of stay in one language, you're just going to get some faster wins there because that language has some awareness of its internals. We do think that there's a lot of room for future improvements, whether it's tiny GraphQL with JIT enabled or YJIT enabled, or maybe even like a Rust-based parser. We really think like we can get this down to like a millisecond or less. So like less than 5 is much better than it was, but we still have room for improvement. So I just encourage you, if you do work in the open source community or you use stuff from the open source community, feel free to make contributions. Just because it's there doesn't mean it's the fastest thing there. And I'm sure they would welcome your contributions and experimentation. After we lex and parse, the next common thing that any GraphQL server will do is validate. So we have our abstract syntax tree. We need to validate it against our schema definition. Are we using valid arguments, types, and fields? We're not really considering variables at this time, but just doesn't make sense according to the spec. One nice thing with validate is actually doesn't even need to talk to the server. You can actually validate your GraphQL operation client side once you have the schema.
Okay, now that you're talking about validation, let's talk about static analysis. So static analysis is used everywhere. It's a way to get insights from code without running the code. For example, here we have this method. There's something weird with this method. And you don't need to run this method to spot it. So what's going on here is that the month argument is not being used. That's something very common that we see in code editors. Sometimes they gray out things that you're not using. And tools like ESLint, Robocop, and some typing systems, they analyze your code without running your code to get some insights. And that's basically how we do validation in GraphQL. We compare our operation with our schema without running the code, so we can, for example, validate the query. In this case, the product doesn't have a name field. Maybe the client is looking for the title field. So this query is invalid, so we don't even bother executing this query here.
So as part of static validation, we are validating the rules according to the specification. Not all rules are actually created equal. So one of these slower rules actually is field selection. It's really influenced by the number of fragments you have. So just to kind of highlight what this rule does, the rule states if multiple field selections with the same response names are encountered during execution, the field and arguments to execute, the resulting value should be unambiguous. Therefore, any 2 field selections which might both be encountered for the same object are only valid if they're equivalent. So in the top left example, we have a query that does actually merge correctly. So in the case of cat, we have 2 occurrences of the same volume alias. So that actually merges into 1. Your response only has 1 occurrence of volume, meow volume. So that's part of field selection's validation process. And then additionally, cat and dog are mutually exclusive. We can't have them both occur at the same time. And because volume, both for bark volume and meow volume are a type int as a leaf type, they can also be merged together because they have the same arguments for both and the same outcome values. In contrast, on the bottom example, the conflicting fields, some value might be a string or an integer, and that's an ambiguous response from the server. It could be a string in some cases, it could be an integer in another case, so the spec says this is disallowed. The big thing here is that it's non-linear to calculate this behavior. You have to walk through the entire tree, and that's quite costly. Back in 2019, Simon Adamant wrote about his deep dive into this validation rule in the GraphQL Java space, and really just highlighted how the old algorithm, this blue line, wasn't as exponential. As you added more fragments, it took a lot longer. So again, for our checkout example, we had a lot of fragments, so we were seeing a longer time to lex and parse and validate. So by using a newer algorithm, is a lot more linear. So in this case, the graph is actually logarithmic scale. So it became a lot safer to handle in a more predictable way, different fragment counts. So this graph is a little bit skewed because it's really highlighting the shortcomings of the old algorithm. Your real-time production data might look a little bit different, but I think it's still a good demonstration that this rule can be quite costly. To help on the performance side of things, if we can actually even not lex, parse, and validate, we can actually speed up our entire response time. So whether you're using a cache or something like persistent queries, the idea is that you're remembering something that's valid and perhaps even remembering the AST. So not all persistent query implementations actually store the AST. Quite often they're storing the string. So that's one thing to keep in mind. If you're storing the string, you generally end up having to lex and parse it again. And that's going to take you some time. Additionally, if you're storing persistent queries, you're going to have a lookup cost to your data store. So you might find that that cost is actually higher than just redoing the lexing and parsing for each small query. So this isn't necessarily a silver bullet. So just be cautious because there are some trade-offs, and it's about finding the right heuristics of when to use which case. Also for validation, we had a win in terms of we introduced an API gateway. This gateway is Rust-based, but our backend code, our servers were Ruby-based. So we actually decided to do the static validation closer to the edge or at the edge. So we could fail faster. We actually had a faster implementation of static validation too. So in our case, the Rust gateway's P99 response time was actually faster than the Ruby server's P50. So we went from basically like, say, 50 milliseconds P99 to 2-3 milliseconds P99. So that's a much drastic change, really a magnitude difference. So like, I don't want to give Rust all the credit, but I think it is certainly a factor.
All right, so now that we saw so many steps of execution, we don't have to limit ourselves to use static analysis to validate queries against a schema. You can use this step to optimize the execution to your app needs. So it's possible to, by analyzing operations, choose the best execution strategy. So one example here is that it's very common for applications to have rich replicas. So you have a primary database that can read and write, and you have other database instances that can only read. Those rich replicas are sometimes underutilized. Sometimes they're only used for data analysis, maybe some reporting, but they're not very often used for actually fulfilling API requests. So one strategy is, okay, in GraphQL, we have queries and mutations. You can say, I can execute my queries on rich replicas and my mutations on my primary that can write. That sounds good, but in reality, it's very possible to have fields that write to the database. For example, here we have a shared URL field, and this shared URL is lazily created. So we don't create URLs for people to share until someone asks for this URL. So it's common for queries actually write to the database. So how can we solve this problem? So something that you can do is create, for example, a custom directive. You can create a directive, for example, here called writer, and this directive is applied to field definitions, so they live in the schema. And now you can tag, you can mark your fields that write to database with this writer directive. And then when analyzing your queries before executing, you can apply your own logic. For example, here we have the shared, the shared URL in this query, so it's not possible to execute in redirect because this query actually needs access to the writer database. But this query doesn't have any fields that with the writer directive, so you are good to use your redirect replicas to execute this query. And you can implement any kind of logic that suits your needs. For example, here we can create some steps. First, we analyze, is this a query, is this a mutation? So we know if it's a mutation, we can't use the read replica, so you can just discard. But if it's a query, you go to the next step. If there are no fields that are marked with the writer directive, that sounds good, right? And also, third step, it's also like more on the operational side. Read replicas have replication lag. It's usually very fast, but if your platform is under heavy load, maybe it takes a couple of seconds. So it's up to you to choose how much replication lag is acceptable for you. So if the replication lag is okay, so now it's safe for you to execute this query using the read replicas. And that's very nice because you can have faster queries because you are using a database that is under, is not under like a heavy load. And also by shifting some of the load to these read replicas, you are giving less load to the primary database that's used by the mutations. So you're also improving the mutations by doing this.
So after we've done our lexicon parsing validation, maybe a custom analysis, the most common well-known phase is execution. So if we consider an example like this, where we have a product, we're fetching it by ID 123, we're gonna get the title, the description, and associated product images. We have two key entities here, a product and its associated collection of product images. We kind of have a familiar resolver waterfall where we have something around the product. The product has the need to then resolve the title, description, and images with URL, alt text, and so on and so forth. So let's kind of look into some strategies that people use to have a sequence of resolvers. So one common thing I see is people deciding to load data by entities. So our first entity that we encounter is a product entity. So we're going to resolve that, perhaps through a data loader. And then after that, we are fetching our product images. So when we're getting our product, we're getting all of the attributes, the title, description, and anything else that exists on the product. So we can easily resolve that. We don't have to make subsequent data accesses. And then it's also the product images. We're getting all of the data for the product images for the product 123. The thing that I want to highlight here is we're asking for all the attributes or all the fields, the columns. So in a way, this is kind of like overfetching. The client has given us their data requirements. They've said that I only care about the title and description, but we still go to the data layer and ask for everything, just in case. So one thing that we can do is use selection sets or look ahead. So here the idea is the resolver can actually tell you what fields under it are asked for by the client. We can use this to optimize our data access. So we're being a bit more selective. And when we go to our data layer, we're telling them, these are the things I care about. So in practice, this might look something like this, where we really just focus on the product resolver at the query root. So here we have the 4 arguments of a resolver function. We have the parent object, which is in this case null. We have the arguments, so ID 123. We have our GraphQL execution context. And the fourth argument is commonly overlooked. It's called the info or GraphQL resolve info. Contains a lot of metadata about where we are in the execution tree. And one of those things in that object is selection set. So it tells you what fields are selected. So we could have a helper like get selection set. That's going to give us an array that says you've asked for the title and the description and the image's URL and the image's alt text. So then we can have a little bit more logic in our resolver function that says I'm going to be a bit smarter about how I get my data. If I know I'm asking for images, I can say get me my product and images at the same time with one round trip to the database. Again, you can still have a data loader under the hood to do all of this, but it's really just that we're giving extra hints to the data layer. And at the end of the day, you might see the SQL query kind of like the bottom. We're being very specific about asking for the product title and description, and then also getting the URL and alternate text back. You don't have to go like super far with this pattern. You might have diminishing returns over time, but really the idea is you can give the data requirements that the client gave you further down your tech stack, closer to the data access layer. Another thing for us was about reducing the number of round trips to the database. With ORMs, they're very powerful, but sometimes you don't always realize when you're accessing the ORM and getting data back. You don't always know when you're accessing remote data. So we actually just have some common test cases that we run on like every field and every type. So we say for all these fields, if we have not already annotated them as allowing data access, we should be asserting that no data access is triggered. So again, just trying to reduce the number of round trips that we have to the database and consolidating them and being very deliberate about the access patterns that we have. I think a strong feature that we're interested in is both compiled queries and planned execution. So trying to basically make this more automatic. In the resolver example I showed, there's a lot of human work done to fetch all that data. I think if we can make the machine smarter, there's a lot of interesting work I think happening in the community right now. We're not very far along in this journey ourselves, but I know I'm definitely following along and considering how we can make that and apply that at Shopify.
All right, now that we went through all phases of execution, let's go a level deeper and see what's going on at the programming language level. So if you're using a programming language that is garbage collected and you profile a GraphQL execution from the request to the response, it's common for you to see those gaps in the execution. And it's interesting because those gaps are kind of the same size except for one on the right, but there's something going on here. So if you zoom in, you can see those pauses are garbage collection pauses. So the memory usage of the process goes beyond a threshold, and the execution pauses, frees some memory, and then resumes. And this can take a lot of the server execution time. For example, for this one, we spent 24 milliseconds on garbage collection, what's more than 6% of the server response time. And what's happening here is we have like the memory usage on the graph on the bottom. So every time we reach this threshold, the execution pauses, does some of the garbage collection, and resumes. But notice that we start our request very close to the threshold. Like we started in a position that's not the most favorable here. And what's going on here is that you have a process that gets a request, process, and gives the client a response, and then waits for the next request, and so on. So what's going on here is that you are inheriting the memory allocation of the previous request. So you already started very close to the threshold. So very quickly, the garbage collector is activated and pauses your execution. Even though you don't need this memory anymore, this memory is not being used, it's from the previous request. It's just waiting for the garbage collection to free up. So what you can do, because we have many pauses happening while the API client is waiting for your response, because that's the moment where the work is being done, most of the memory allocation is being done is during this part of the execution, and this is our critical path. The client is waiting for you to respond. Something that we can do, we can force garbage collection to happen between requests, not while the client is waiting for the response. So just after we send the response to the client, okay, the client's not waiting anymore, so now we can trigger the garbage collector and free this memory. So the next request won't have that many garbage collection pauses. So we can go from a situation like this, where a lot of garbage collection pauses happen while the client is waiting, to another scenario like this, where we are shifting all the garbage collection for just after we send the response back, we trigger the garbage collection. So those 24 milliseconds that the client had to wait for us to free memory is drastically reduced. All right, so if you have any feedback, you can scan this QR code. We'll have a topic table tomorrow. We'd love to hear from you, and thank you very much.